Hi, and welcome to 8.01 Half-Life and Radioactive Decay. These are the Common Core standards that we will be addressing in this lesson. They are found in Course Information. Click on Standards. The lesson standards and objectives are found in the Lesson Introduction tab. We must understand what the difference between a chemical reaction and a nuclear reaction is. In chemical reactions, we are basically just sharing or transferring the valence electrons to form new compounds, such as a covalent compound or an ionic compound. Remember, we're only changing the valence electrons. The nucleus in a chemical reaction remains the same. We're not changing the number of protons or neutrons at all. The chemical will have the same chemical identity of the individual atoms. Therefore, oxygen still has a chemical identity of oxygen. Whether it's bonded to hydrogen or to another oxygen, it's still oxygen. Nuclear reactions are a little bit different. They have unstable nuclei because of the ratio of protons and neutrons. Sometimes that ratio just becomes too off balance and the nucleus is unstable and it's going to fall apart and break. And that's what we call radioactive decay. The nucleus is going to break down in nuclear reactions, forming a whole different chemical. So oxygen could fall apart and form something else. Oxygen really doesn't do that too much though. Uranium can fall apart and form something else. That happens a lot more often. Different number of protons in the nucleus means a different element. Recall that your atomic number on the periodic table tells you how many protons you have, and it tells you the chemical identity. Alpha particles are represented by the Greek letter alpha. It is basically a helium nucleus. Alpha particles are basically just a helium nucleus. We represent helium nuclei with this isotopic symbol. Remember your isotopes. We have the chemical symbol He, and then we put at the top the number 4 because that is the mass of the helium nucleus, 2 protons, 2 neutrons, and the atomic number of helium is 2. An alpha particle is basically just a helium nucleus. So this is how we represent it. Write it down, you must know that. An alpha particle is positively charged because the electrons are no longer there. It has high kinetic energy and can cause damage to surface materials such as skin and living tissue. Relatively easy to shield against. Alpha particles not too dangerous. It normally cannot penetrate lightweight materials such as paper or fabric. Radioactive materials are used in smoke detectors. So your smoke detectors uses alpha particles. And as the smoke comes in between the radioactive source and the sensor, an alarm goes off. Beta particles. We represent them using this B, the Greek letter beta. It is basically when a neutron from the nucleus falls apart and it forms an electron, which is what the beta particle is, and a proton. We can use these isotopic symbols to represent a neutron, N, with a mass of 1, 0 atomic number. An electron has a 0 mass, and we will put a -1 down here because it's kind of like the opposite of a proton, if you will. A proton has mass of 1, and of course it has 1 proton because it is a proton. Beta particles, which is this symbol right here, beta particles are negatively charged. Basically, they're a high-speed electron. They're going to move faster than alpha particles. They are more difficult to protect against, and they can penetrate cloth and paper. Beta particles can penetrate deeply into your skin and potentially harm or kill living cells. Once they land on your skin, they can be absorbed by any material. They really cannot penetrate thin layers of denser materials such as aluminum and other metals. Beta particles are finally stopped by a substance. They can be and will be absorbed by that material, just like any other electron. Gamma rays we use this gamma symbol. It's Greek letter gamma, kind of like a Y. They are a form of electromagnetic waves with very high frequency and high energy. They're the most energetic of all electromagnetic radiation. They have no mass and no charge. 0 mass, 0 charge. They can penetrate pretty much through almost anything. Gamma rays can cause much more damage to living cells than alpha or beta particles, and only dense materials like thick layers of lead and concrete can stop a gamma ray. And that's why when you have an X-ray in a hospital, you have to wear that lead vest just to make sure that the gamma rays don't penetrate other parts. Here's an overview of alpha, beta, and gamma from your lesson. Please make sure that you are able to compare and contrast via multiple choice and essay format all three types of radiation. Like I said, this is located right in your lesson. It's everything I've already gone through, but please make sure you do understand the difference between the three. And as a review, I would like for you to take these problems and right next to it, identify each as alpha, beta, and or gamma radiation. It could be just one, could be two, could be all three. And pause this recording so that way it gives you ample time to practice and try these and go back and look up if you need. And when you're ready to resume, hit play. Welcome back. A. Stopped by lead. Well, really, alpha, beta, and gamma are all stopped by lead, aren't they? All three of them can be stopped by lead. Smoke detectors. Which one is located in smoke detectors? That was alpha. Causes an atom to lose a helium nucleus. Remember, that's an alpha particle. Which one is the slowest moving? Once again, alpha. Alpha is the slowest and the least dangerous. Which type of decay has a neutron that breaks down into an electron and a proton? That was our lovely beta decay. Which one can kill living cells? Alpha, not so much. Alpha's pretty safe, so for our official answer, we're going to put beta and gamma. Both of those can kill living cells. Which one will be absorbed by the substance that stops it? That was beta. Remember that if a beta particle is stopped by your skin, it still will be absorbed by it. Which type of decay is where the nucleus gains a proton? That is our beta decay. Which one is the easiest to protect against? Alpha. Alpha's pretty safe compared to the others. Which one has the greatest amount of energy? That is our lovely gamma rays. With radioactive decay, we must be able to write nuclear equations. These are similar to chemical reactions in that we have reactants and products. However, with nuclear reactions, we actually have alpha particles, we've seen those, beta particles, and a mystery particle. In nuclear equations, we will actually take this chemical and change its identity. But there's still something that's nice. The mass number that's at the top, the left side of the arrow, must equal the total on the right side of the arrow. And that is because mass is still conserved. 239, we must still have a total of 239 mass at the end. So the total of my products must still have the same amount of mass as my reactants. My atomic number must remain the same. The total. 94. The total on the right must equal the total on the left. Please pause this recording and try this one on your own using the previous example to help end your lesson. Welcome back. We have the alpha decay of uranium-238. Uranium is U. 238 is the mass. Remember how we write our isotopic symbols. And then we look at our lovely periodic table and we see that uranium has an atomic number of 92. Since this is alpha decay, we know that the alpha particle is the helium nucleus. And remember how to calculate this final product. What does uranium-238 turn into? Well, it's going to release an alpha particle out of its atom. The uranium is going to turn into something else. But remember, the total of the top must be equal. So on the left side of the arrow, we have 238. That must be equal to the total on the right. So if the alpha particle has a mass of 4, my mystery particle has to have a mass of 234, because 234 plus 4 equals 238. Same with my atomic number, 92. I have 92 on the left. My alpha particle has an atomic number of 2. My mystery particle plus my alpha particle must have the same atomic number as the left side. So 2 plus 90 equals 92. We use the 90, we look up on the periodic table, and we see that this is element TH. This is alpha decay, and we're going to form thorium-234. Please pause this recording and try this example. Welcome back. This is thorium-234, so I know 234 is going to be there. We look up on the periodic table for thorium-234. We know it is element number 90. This says beta decay, so we know our beta particle is that. And now we have to figure out what our mystery particle is. Remember, the total top must be equal on both sides of the arrow. 234, since the beta particle doesn't have a mass, that means my mystery particle still has 234. The total of my atomic number must be equal. 90 on the left. This one's a little bit different, isn't it? 90, and then we have -1 plus our mystery. So if we rearrange, we put -1 on the other side, turns it into a positive. And this is just simple algebra here. We know our mystery particle has an atomic number of 91, which is element Pa. Remember, total top number right side must equal total top number left side. Total bottom number must equal total bottom number left side. Okay, one more practice problem. Let's have you try this decay on your own. Please pause this recording. You should be able to do this with no problem. If not, you may need to rewind and go over the practice problems again. Welcome back. We see that this is americium-241. We know we see this particle right here, and this is what tells you what type of decay it is. Hopefully by now you recognize that as alpha decay. And now we have to figure out what our mystery particle is. We can start with the top number or the bottom number, does not matter. I'm going to start with the top number. I know I have 241 on the left side, and that must equal the total top on the right side. My alpha particle has a mass of 4, therefore my mystery particle must have a mass of 237, because 237 plus 4 equals 241. Now on the bottom, americium has an atomic number of 95, so that must equal the total of my mystery particle plus 2. So my bottom one must be 93. So my mystery particle must have an atomic number of 93, and when we look that up on the periodic table, we see that my mystery particle is neptunium-237. Half-life. Half-life is the time it takes for half of your sample to decay. When we're thinking of alpha and beta reactions, we know that our nucleus is falling apart and it's forming an alpha or beta particle as well as another mystery particle. Each chemical and each element has a unique half-life. Not every element in the world falls apart at the same time. Some elements are pretty stable, so it takes a lot longer for the nucleus to fall apart. Some elements are very unstable and their nuclei will fall apart very quickly. We will represent the half-life by lowercase t with a subscript of 1/2. Remember, half-life is a time. How long does it take for half of your sample to fall apart? An example, half of a given sample of radium-226 will decay into lead by the end of 1,620 years. That means the half-life is 1,620 years. If we had 100 grams to start with, after one half-life, we would have 50 grams remaining. And then after another half-life, we would have 25 grams remaining. And after a third half-life, we would have 12.5 grams remaining. So every time it cuts in half, that equals 1,620 years. So this is 1,620 years. This is another 1,620 years. And this is another 1,620 years. So it takes a long time for radium-226 to go from 100 grams to 12.5 grams. We can graph the half-life. All half-life graphs have similar features. We have the time on the x-axis and the amount on the y-axis. The slope is going to be negative and it's sharp in the beginning. And this is because we start with a lot of our chemical, like 100, and then it quickly reduces. 100 to 50, 50 to 25, not so much of a drop, right? On this graph, we can start off with, let's say, 1 of your substance. After 1 half-life, it's going to be 0.5. So whatever time this is, that's the half-life of your substance. That is half of your sample. We have 0.5 after 1 more half-life. Now remember, half-life is the same. If this is 100 years or 2 million years, 2 million years, each half-life is the same. So whatever this time is, it's going to be consistent. Notice the scale on the x-axis remains the same. And notice that the area under this gets smaller and smaller, and it will level out eventually. What is the half-life of a substance if it takes 1,200 years for a 100-gram sample to decay to 12.5 grams? Pause this recording and get as far as you can on this as you can. If you need to rewind and review what half-life is, feel free to. Welcome back. What is the half-life? So it's asking for what is the half-life of a substance if it takes, so the total time is 1,200 years. For a 100-gram sample, that's our first mass, is 100 grams, to decay to 12.5. So that's our final mass. Basically what we have is we have 100 grams, and half-life said that it's going to be cut in half. So that goes to 25 grams, and then eventually to 12.5 grams. What we have to figure out is how many half-lives was this? Well, 100 grams to 50 grams is one half-life, 50 to 25 is a second half-life, and 25 to 12.5 is a third half-life. So we undergo 3 half-lives. The total time, remember, the total time was 1,200 years. So we have 1,200 years divided by 3 because we have 3 half-lives, and that equals 400. So my half-life is 400 years. So every 400 years, my sample is going to decay by half. Please pause this recording and try this last practice problem. Welcome back. How long does it take for a substance to decay from 138 grams to 34.5 grams if its half-life is 25.9 days? Alright, so this one we know half-life is 25.9 days. We know the initial mass is 138 grams. We know the final mass is 34.5 grams. We need to figure out how many half-lives did it undergo. So 138, and then we have to figure out, okay, what is half of 138? So 138 divided by 2 equals 69. And then half of 69 is 34.5 grams. So this underwent 1 half-life, 2 half-lives. And each half-life is 25.9 days, but we had 2 half-lives, so we have to multiply by 2. So 25.9, and that is it for alpha and beta particles, gamma rays, and half-life. Thank you. Have a great day.